Hey everyone, and welcome back to the channel. Today we're diving deep into one of nature's most powerful and awe-inspiring phenomena, tsunamis. We often hear about them in the news, these colossal waves that can travel across entire oceans. But have you ever wondered what really triggers them? While landslides and volcanic eruptions can cause tsunamis, the vast majority of the most destructive ones are born from something happening deep beneath the ocean floor, massive earthquakes. So what's the connection? It's all about movement. Our planet's surface is made up of tectonic plates, giant puzzle pieces that are constantly, slowly, grinding against each other. When the stress between these plates builds up and is suddenly released, we get an earthquake. But not just any earthquake can create a tsunami. It typically requires a quake of at least magnitude 7.5, and it needs to happen under the ocean, causing a sudden vertical shift of the seafloor. Imagine you're in a bathtub and you suddenly shove your hand up from the bottom. What happens? You displace a huge amount of water, creating waves that slosh around. That's essentially what a powerful undersea earthquake does, but on an unimaginably larger scale. An entire section of the ocean floor can be thrust upwards or dropped downwards by several meters in a matter of seconds. This vertical displacement shoves the entire column of water above it, from the seabed all the way to the surface, launching a series of powerful waves in all directions. This is exactly what happened on December 26, 2004. A monstrous magnitude 9.1 earthquake ruptured along a fault line off the coast of Sumatra, Indonesia. This was a megathrust earthquake, where one tectonic plate slid beneath another. The seafloor was violently uplifted, displacing a colossal volume of water in the Indian Ocean. The resulting tsunami was one of the deadliest natural disasters in recorded history. The waves radiated outwards, devastating coastal communities in 14 countries from Indonesia and Thailand to as far away as Somalia on the east coast of Africa. It was a tragic and powerful demonstration of how an earthquake's energy is transferred to the ocean. But this wasn't a one-off event. History is filled with examples of this deadly partnership. Let's travel back to 1960. The Great Chilean Earthquake, the most powerful earthquake ever recorded at a staggering magnitude 9.5, struck off the coast of southern Chile. The rupture of the Nazca Plate subducting under the South American plate caused widespread devastation on its own. But it also generated a massive tsunami that not only battered the Chilean coast, but raced across the entire Pacific Ocean. Waves reached Hawaii, Japan, the Philippines, and even New Zealand and Australia, causing damage and loss of life thousands of miles away from the epicenter. This event was a major wake-up call for the world, leading to the creation of the Pacific Tsunami Warning System. Fast forward to a more recent event, March 11, 2011. A magnitude 9.0 earthquake, the Tohoku earthquake, occurred off the coast of Japan. The immense energy released caused a section of the Japan Trench to lurch upwards. This unleashed a devastating tsunami with waves that reached heights of over 40 meters in some areas. The images from that day are seared into our collective memory. The tsunami overtopped seawalls and traveled miles inland, causing immense destruction. It highlighted that even for a country as prepared for earthquakes as Japan, the power of a tsunami generated by a top-tier earthquake can be overwhelming. So we see a clear pattern. A massive, undersea earthquake involving vertical displacement of the seafloor leads to a significant, often catastrophic tsunami. The bigger the quake and the more the seafloor moves, the more water is displaced, and the bigger the resulting tsunami waves. Think of it as a domino effect. The initial slip of the tectonic plates is the first domino, and the final devastating wave hitting a distant shore is the last one in a very long line. It's fascinating to understand the physics at play. Out in the deep ocean, a tsunami might not even be noticeable. It could be a long, low wave, maybe only a meter high, but its wavelength, the distance from one crest to the next, can be hundreds of kilometers long. This wave travels at incredible speeds, comparable to a jet airliner around 800 kilometers per hour. As this fast-moving wave approaches a coastline, the ocean becomes shallower. This is where things get dangerous. The friction with the seabed slows the front of the wave down, causing the water behind it to pile up. The wave loses speed but gains immense height, transforming from that low, fast wave into the towering wall of water we associate with the word tsunami. The 1700 Cascadia earthquake is another compelling, albeit historical, example. For a long time, there were indigenous oral traditions in the Pacific Northwest of a great earthquake and a giant wave that wiped out coastal villages. But there was no written record. Then, scientists studying geology in the region found evidence of a massive, sudden land subsidence. At the same time, researchers in Japan were puzzled by historical records of an orphan tsunami, a tsunami that struck their coast in January 1700 without any preceding earthquake being felt in Japan. By connecting the dots, the geological evidence in North America and the historical records in Japan, scientists concluded that a massive magnitude 9.0 earthquake must have occurred along the Cascadia subduction zone. This quake dropped the coastline and sent a tsunami racing across the Pacific, hitting Japan hours later. It is a brilliant piece of scientific detective work that proves this earthquake-tsunami link has been a powerful force of nature for centuries. Understanding this link is not just academic, it's crucial for survival. It's why tsunami warning systems are so heavily reliant on seismic data. When a large earthquake is detected under the ocean, agencies like the Pacific Tsunami Warning Center spring into action. They use seismic sensors to determine the quake's magnitude, location, and depth. They then use models and data from a network of deep ocean buoys, called dart buoys, to detect if a tsunami has actually been generated and to forecast its path and arrival time. This information gives coastal communities precious time to evacuate to higher ground. It's a system built directly on the scientific understanding of the relationship between earthquakes and tsunamis. So the next time you hear about a major earthquake near a coast, remember the bathtub analogy. The shaking ground is just the beginning. It's the silent, massive displacement of the seafloor that transfers that incredible geologic energy into the ocean, creating waves that can carry that energy across the globe. It's a powerful and humbling reminder of the dynamic and interconnected systems that shape our planet. It's science that helps us understand these forces, and most importantly, helps us stay safe. Thanks so much for joining me on this deep dive today. I hope you found it interesting. If you enjoyed this video and want to learn more about our amazing world, please hit that like button, and don't forget to subscribe and ring the notification bell so you won't miss our next adventure. See you in the next video.